Hi everyone, I hope you're enjoying the snow day, but as you probably already know by now, we're still holding you all responsible for doing the worksheet and analyzing the data for the lab that you'll be missing today. So I thought I'd give you a little pre-lab lecture, basically with the lecture that I'll be giving to my section on Thursday, um, just to give you guys a little bit of help in interpreting the data and writing up your worksheet. So the data that you'll be getting will be from my sections, my Thursday morning section. Either me or your instructor will be emailing you the data, and it's going to be your responsibility to process that data and then use that data to write up your worksheet. So why don't we get started? So we're going to be talking about the rate of reaction of oxygen and iron. So it's a familiar reaction that I think most of us are used to seeing in at least everyday life, but it's the idea of iron reacting with molecular oxygen to form rust or iron oxide, right? So we're going to be using the change in the volume of oxygen to examine the kinetics of this reaction between the iron and the oxygen. So in general, we know this reaction is actually kind of slow. You don't leave out a piece of metal and then you come back in the morning and it's just rusted to death, right? So we know it's a kind of a slow process. But in this particular lab, we're looking at the same process, but we're going to be using a catalyst to speed up that reaction. So we've already talked about in lab how a catalyst, it can change the reaction path, so it actually lowers the activation energy. So it's going through a completely different reaction mechanism, but that the K, the rate constant of that reaction, is faster than if there was no catalyst around. So our catalyst is going to be acetic acid, because we know if we waited for a piece of steel wool, which is going to be used in the experiment, to sit there and rust at its normal rate of atmospheric pressure and regular ambient temperature, we're going to be in lab for a very, very long time. So what we're doing is using acetic acid. It's taking it through a different reaction mechanism, but the overall reaction is going to remain the same, in which iron reacts with oxygen to create iron oxide or rust. So if you were actually doing the experiment, a piece of steel wool would be treated with acetic acid, which is our catalyst, and it's going to be placed into a graduated cylinder that's inverted into a beaker of water. So as the iron in the steel wool reacts with the molecular oxygen in the air, what's going to happen is that it's a change in the partial pressure of oxygen, right? And so there's going to be less pressure inside the graduated cylinder. If you notice on the outside, right, we have it opened, the water surface is exposed to the atmospheric pressure. That's going to exert a pressure on the water, which exerts a pressure inside the graduated cylinder that'll eventually hit equilibrium. So the inside of the cylinder will be at 1 atmosphere of pressure. What this does is it forces water up into the inverted graduated cylinder. And we can measure that change in the water from basically, what was it from the start of the experiment, and how that water gets sucked up into the test tube, the inverted test tube, right? We'll know that volume change, and since that volume change associated with the water can be associated with the oxygen, we actually can calculate how many moles of oxygen are being consumed over time. So here's more of a schematic drawing, right? We start at t equals 0, so times 0. So we can see that, so the actual iron itself is not shown in the picture, but you can see you have your inverted graduated cylinder. It's filled with air. Air we know is 20% oxygen, so there's enough oxygen around to be reacting with the iron. And we see the water level inside the test tube is equal to the water level in the beaker that the test tube was inverted into. So then we have this second figure where it says at time t. I don't know what t is, right? It's some time in the course of the experiment. So it applies to any of your intermediate points between the beginning and end of the experiment. As that oxygen reacts with the iron, right, we saw previously that it forms a solid. So you're pulling gas in the form of molecular oxygen out of that environment. It's reacting with the solid iron and becoming solid rust or iron oxide. So that's reducing the volume of oxygen inside the test tube, which reduces the partial pressure. That pressure needs to equalize with the atmospheric pressure, and what that does is it pulls the water level into the graduated cylinder. So we can measure that as a height. So if you were doing the experiment, you would have a ruler taped to the outside of your graduated cylinder. We'll talk in a second how we can convert height into delta V, which is our change in volume, which is the change in the volume of water, which is also equivalently the change in volume of the oxygen. At the end of the experiment, there will be no more oxygen left inside the test tube. The reaction ceases because iron is not going to react with carbon dioxide or nitrogen, so it becomes inert at this point. And we've reached our total height, which we're going to call H max, so the maximum height that water can be pulled into the test tube, which means all of our oxygen's gone. And we'll talk in a second again how we can convert H max into that delta V max, our maximum change in volume. So we're going to use the height of the water column to calculate the change in volume of water, right? This is going to give us a change in volume of oxygen, right? So we can calculate the moles of oxygen at each time reading using the ideal gas law. So again, I'm going to give you a lot of this data. I shall give you all the data, but I'm also going to give you the room temperature and the pressure inside the room. More than likely, it's probably going to be in inches mercury. We've all looked at the barometer. It's an imperial unit, so I'll probably give it you in that. You're just going to have to convert that to atmospheres. But knowing the temperature of the room, the ideal gas constant, and the pressure in the room, right, we can calculate the concentration of oxygen each time reading by dividing the moles of oxygen by the volume of oxygen in the graduated cylinder, right? So be careful here, right? Not only is the oxygen being consumed, but the volume of the reaction vessel is decreasing as the reaction proceeds. What does that mean, right? When we're processing this as data, that means each data point is actually going to have a different volume, right, and a different height associated with it. So when you are making an Excel file, make sure you're paying attention to when you're creating these equations that they actually make sense. Because we've seen before when you're pulling down, like if you write one equation, you try to pull it down, and some things need to remain constant, and if you don't use those dollar signs in front of the cell number and the cell letter, that it can mess everything up. So just make sure you're paying attention to the equations that you write in Excel, right? So you're going to be making a chart in Excel that looks like this. So you're going to have your clock reading, which is just the time, right? You're going to start at T0 and you're going to go to the end of the experiment, whatever that is. It is a slow reaction, even with the catalyst. So we're going to be doing time, most likely. If you want, you can turn it to seconds, but it's convenient to use minutes. The height of the water is either going to be measured in millimeters or centimeters. Make sure you're keeping track of your units. And then this is what I alluded to earlier, the idea that we're going to be measuring the height of this water column, but using basically, what is this, 3rd or 4th grade geometry. We know that the volume of a cylinder, well, actually we can go even simpler. The area of a circle is just pi r squared, and the volume of a cylinder is just taking that circle and multiplying it by the height. So the change in volume, because the graduated cylinder is cylindrical, delta T equals pi r squared times the height. And if you notice there in the 3rd column, it has this subscript T. That doesn't stand for total, that just stands for the change in volume at time T, whatever that is. We're going to have several time points. And the same idea, pi is a constant, r squared is a constant, because r is just the radius of the graduated cylinder. That's not going to change. But the height also changes, because that's why we now have height, the h sub t, so the height at whatever the time interval is. So if we take a look at the equations that are being used here, you see for the first 3 columns it's pretty straightforward, but you just kind of like what we did with the Clausius-Clapeyron lab, you're going to need to also solve for your final values. Specifically, you're going to need to solve for delta V max first. Because if you notice in the 4th column, when we're solving for moles of oxygen, or N sub O2, right, we see that part of even the very first equation where it says N sub naught equals P delta V max over RT, well, there's our delta V max, right? So we need to know what that maximum amount of NO2 is. And you might be wondering, like, wait a second, that's T sub 0, which is at T at time 0. Why am I using delta V max if that's the end of the experiment? You need to remember what we are measuring, right? We're measuring the change in water, and we're relating that to the change in the volume of oxygen that's being consumed. So we said at the very end of the experiment, all the oxygen is consumed. So we can make the assumption that that change in V max, right, the delta V max is actually equal to the total volume of oxygen that we started with. So it's kind of backwards logic, but you need to realize that we're starting with all the oxygen we can start with, and at the end we're measuring that delta V max, which is corresponding to the starting volume, the maximum starting volume of O2. So maybe think that over a little bit, make sure that makes sense, because you see as you go down in the rows, we see n sub 1 equals P times delta V max minus delta V1, right? So what is that saying? Inside the parentheses, it's saying, well, I started with the maximum amount of oxygen, some of that was consumed, right? And so there was a subsequent volume change. So that little bit of oxygen that was consumed at the first time point, right, that needs to be subtracted from the maximum amount of O2 that there is, and it tells you how much oxygen was in that little sliver of that volume change. So that's what we're trying to calculate, right? So we go through, you're going to apply that to every single time point. In the end, right, again, and this is what I was giving you that warning on that last slide when we're trying to find out the concentration of oxygen, right? So concentration is going to be moles per volume, so in molarity. But at every single time point, that volume associated with the O2 is changing. So again, you need to keep in mind that the volume of the tube is constantly changing, right? Oh, sorry, 1 second. One thing that was left out, so if you think about the V max, right, delta V max, we can calculate that. Well, that was easy because we're measuring the height of the water. In that last column where it says V tube minus delta V1, well, what is V tube? And you also see there's no delta, so it's not changing. We're going to assume that the graduated cylinder is either a perfect cylinder. We could do that and then calculate from the radius and the height of the entire cylinder what the volume is. Or the other possible way is we could just fill that graduated cylinder with water, dump that into a graduated cylinder, and get an accurate volume of what that graduated cylinder is. So that's what we're going to do. We'll send you the volume of the V tube. But in worst case scenario, you could have always made that assumption that it was a perfect cylinder. It's not, because it has a little bit of that, that bottom is curved, and then calculated the volume that way. So in the end, you're going to end up with a chart that has all of this processed data. And what are we going to do with that, right? We need to remember our integrated rate laws. So what we're going to be doing is taking that data. If we go back, actually, what we'll have is molarity. So if we look at that last column, right, so we have concentration of O2, that's why it's bolded, and we're going to be doing this over time, and we think about our definition of rate. Our definition for rate was the change in concentration of a reactant over time. And that's why we spent so much time in the last couple of classes deriving these different integrated rate laws using that initial assumption that the negative change in the reactant over the change in time is equivalent to the rate. So we had 3 different rate laws that we calculated using calculus, right? The first, maybe I should do this one at a time. The first one, we look at AT, or A sub t, so the concentration of A at some time equals negative K times T, where negative K is the rate constant, T is just whatever time has elapsed since time 0, and plus whatever the concentration that you started with of that reactant. We know that equals Y equals mx plus B, right? So usually, there's no class here, but I ask you, what rate law is that? What integrated rate law does that correspond to? You should all recognize that that's 0th rate law. Then we look at the second one. We also have a second equation where we did out the calculus and found out the natural log of the concentration of A at some time point, so sub t equals negative KT, same KT in the first example, plus the natural log of the initial concentration of your reactant. That's your first order integrated rate law. And then our second order integrated rate law looks like this. So we can go through the same thing. 1 over the concentration of A at some time, right? That's not A total. That's A at time point T. So 1, 2, 3, 4, I don't know what minutes, but whatever time it is, equals, this time remember it's positive KT. So that's the rate constant times the time of whatever is elapsed, plus 1 over the concentration of your reactant that you started with. So we'll notice all of them, right, are in the form of y equals mx plus b, so you can graph them and visually inspect, is this a zeroth, a first, or a second order reaction? Well, what are we looking for? Well, if it's y equals mx plus b, it better be a straight line. So we'll be making 3 graphs, and we'll be analyzing, is it linear when it's graphed as a zeroth order reaction? Is it linear when you graph it as a first order reaction? Or is it linear when you graph it as a second order reaction? I'm going to give you the heads up right now. First and second order reaction are going to look very similar to each other. The zeroth order reaction will be pretty obvious what it is. My recommendation is to use your data points, fit it to a least square, using the least squared method, which means put a straight line through it, have Excel return y equals mx plus b for you. Display the r squared, which is the goodness of fit or the correlation of the data to the line that's being plotted. The one that has an r squared value closer to 1, so one that's closer, an r squared that's closer to unity, which says that that equation really accurately describes the data, is going to be your order of the reaction. Right, so basically this is what I just went through in words, but the idea, if you plot in the concentration of O2 versus time and it's linear, it's going to be zeroth. You plot the natural log of O2 versus time and it's linear, it's going to be a first order reaction. If you look at the reciprocal concentration of O2 versus time, then it's going to be a second order reaction. Pay attention to the, is your K supposed to be negative or positive? So is your slope negative or positive? That will also give you an indication if it's a correct representation of the graph. And again, make sure you use your r squared value to compare how linear the actual equation is. We don't really need to go over safety and waste, right? You guys aren't actually doing the experiment, but in general, do know that acetic acid, right, that can give you, it's not the worst acid you can come into contact with, but it can still burn you, hurt your eyes, and attack mucous membranes. So extra bonus lesson on that one. All right, so that's the end of the slideshow. Remember, if you have issues processing the data or having trouble with Excel, remember, set up office hours either with your instructor or set up office hours with either me or Dr. Sears, and hopefully we can take care of any questions that you have. So again, on Thursday, I will send out, or your instructor will send out, the data that I collect from my Thursday morning lab, and you'll just process their data. And your worksheet will be due 1 week, so your normal lab period 1 week from today. All right, enjoy the snow day. I know it's not much of a snow day since you have work, but we'll see you all tomorrow.